cylindrical. But you have a square copper wire, right, in this question, and the cross-sectional area. So this was the cross-sectional area, right? And this was so this has a 6 millimeter side, which means that area was 6 into 6, right? The wire was 10 meter long and a carrier current of 3.6 ampere was flowing. And the number density of electron was this. So we calculated the current density, which was J. We calculated electric field, and this was the last question. So how much time it required for electron to travel the length of the wire? So that would be whatever the length is divided by distance upon speed. So this was the question that we did. Now we have another question, and in this question you have so just remember that just remember these two things, that the drift velocity is, so this is E tau by m, right? And then this is the current which is related by this drift velocity by this amount, right? Where this n is your number density, right? Number density is how much? Number of electrons and divided by volume, right? So n by p. And then this E was charge on one electron area. So this A is the area of cross section. And then Vd is the average velocity of the electrons, right? So Vd is the drift velocity. So keeping these two things in mind, let us do this question. So we have to calculate the drift velocity of the conduction current of area of cross section into the power -7 meters square, and of copper wire, right, where each copper wire or each copper atom, each copper atom contribute to 1 electron, right? And the current is let's say 1.5 ampere. The density of the copper wire is the density of copper wire is 9,000 kg per meter cube, and the molecular mass, or not the molecular but the atomic mass of copper is, so M is 63.5, right, or gram. So this is the question. What we have to calculate? We have to calculate the drift velocity, right? And what are the things which are given? So they have given the current, which is 1.5 ampere. They have given this area, which is 10 to the power -7 meters square. And they have given the density rho. So this is not number density, because the unit is kg per meter cube. right? This is not per meter cube. So which means that not number of electrons per meter cube. So then this is mass density, right? So rho is given, which is 9,000 kg per MQ. This rho is not resistivity. This is the density, right? And atomic mass is given, which is 63.5 grams. Okay. So now we know that what is the relation between current and drift velocity, right? So this is I is NEA VD, and we have to calculate VD. So this would be I by NEA, right? So what are the things that we have already? We have this I, we have this A, we have this E. Do we have this number density? Yes. We have this number density, right? So we don't have this number density. So goal is to find out number density, right? And to find out the number density, right? We have to find out the number of electrons, number of free electrons, right? And this number density is number of electrons divided by volume. And we know that for per meter cube volume, so for meter cube volume, the mass is 9,000. So volume is also given. Volume is 1 meter cube, right? So ultimately, we have to find number of electrons. And this is 1 meter. And what is else which is given? So this is given that each copper atom contribute to 1 electron. So if I want to calculate number of electrons, then what should I calculate? Yes, guys. I have to calculate total number of electrons, right, in a copper wire. So this is given that number of, yes, Shaved. Yes, Shaved. What did you say? So you see that each copper atom contribute to 1 electron, right? Q by E. Q by E. What is Q by E? Yes. Oh, you are saying that Q is equals to N is number of electron is Q by. But I don't know this charge, right? I don't know this charge. So I have to use that number of copper atoms. So number of electrons is equal to the number of copper atoms. Is this part clear? So if I calculate the number of copper atoms in the wire, that would be easy to calculate, right? So if I want to calculate a number, if I calculate number of copper atoms, that would be equal to the number of conducting electrons, right? Number of free electrons. Is this part clear? Is this part clear? So to calculate the number of free electrons, I will calculate number of copper atoms. Right, this is the code. So N would be number of copper atoms divided by 1 meter. So this is right. Now recalling the chemistry classes, guys. We have to calculate number of copper atoms, right? So whenever we want to calculate number of copper atoms, so we know that number of particles or number of atoms is equal to mole into Avogadro number.
Avogadro number.
Right? Yes, absolutely correct. So if I want to calculate number of copper atoms, then I have to calculate number of moles, right? And Avogadro number I know. So Avogadro number is 6.022 into 10 to the power 20 number of particles. Right? So I have to calculate this number density, I have to calculate this number of moles, right? And number of moles. So now we will use this information, right? Because number of moles is what? Number of moles is mass given upon the atomic mass, right? So I know that in 1 meter cube volume, the mass is 9,000 kg, right? So mass is 9,000 kg, right? And I have, so this is the mass given. And atomic mass is 63.5 gram. This is 9,000 into 1,000 gram. This is 9 into 10 to the power 6. So now I have this mass given, I have this atomic mass. So then I will have this right. Then I'll have this number of moles, which would be 9 into, which would be mass given, right, divided by this atom. So then this would give us the number of atoms in the copper atom, right? Okay, so this is number of moles, right? And then I want to calculate the number of copper atoms. So then this would be mole, which is 9 into 10 to the power 6 divided by 63.5, and then 6.022 into 10 to the power 20. So this is my number of copper atoms. This was the code, right? This was the code, number of copper atoms, right? Now we have this N, and we have this current, we have this area. Now we can calculate the drift velocity. So drift velocity would be I, and N E. So I is 1.5 ampere. N we just calculated. And we have this E, which is 1.66 into 10 to the power minus 19. And area is how much? Area is 10 to the power minus, right? So all the units are in the SI unit. So first, let us calculate the number. So this is 1.5 into 63.5. And then this is 9 into 6.022. And then 1.66. And then this is 23. And this is 26. Right? So this is 10 to the power, in the numerator I am taking, right? So this is 26 minus 20. This will be negative in the numerator, and this will become positive. So the answer would be how much? So how much is 1.5 into 60.5? This is 95.25 into 10 to the power 3 divided by 9 into 6.0 into 1.89.96. So this would be how much? 95.5 divided by 89.96. So 1.058 into 10 to the power 3 meter per second. This is the drift velocity. So from this velocity, the electrons will, right, the free electrons. Is this part clear, everyone? Yes, is this clear?
Yes.
Yeah, so please note it down, and if you guys have any doubts, please ask, right? Okay, so please note it down. What is kind of Chavez? This is U or gram, right? Or whenever you want me to scroll down, Tariq, please
So this is a G question.
yeah. So this is yeah. This was a very lengthy question. Yeah, did you note down this part?
Yes.
Okay, so already noted. So please down. Whenever you want me to scroll down, please tell me. Okay, where did Chavez? Yes, whenever you have noted it down, please just make it out.
Yes, you can scroll down.
Noted. Whenever we have completed, please tell me.
So for the number of months can you choose 6.023 into interest to 24.
A number of what?
So for the number of modes value 6.03 6.023 can we use.
Yeah, we can use 6.023 or 6.02. Both are
So
nearly.
will we get the same answer?
Yeah, absolutely, absolutely. So because you see that what is the in third decimal place you will get the change, right? So that is nearly 6.02. Both are nearly 6.02, right?
Yes.
So yeah, so in the third decimal place you will get the change, but both are right because this is the order of 10 to the power 20. So this doesn't make it.
So then we can round it off. We can get 1.06 into 10 to 3 meters.
Yeah, when what?
So final answer we can round it off.
Yeah, of course. So we can round it off and we can write this as 1.06. So did you do this problem in your class? You can check that.
No, sir.
Yeah. So did you note down this part?
Yes.
Good. So now we have completed. We have understood that yeah, we have a conductor, and then there are free electrons are flowing, and those are creating some currents, right? And those free electrons are moving with some drift velocity. They are simultaneously colliding, and then there is some relaxation time. So all these things we understood, right? Now we have this next topic is temperature dependence of resistance. Or this resistivity. The graphical portion you have done, so I will do this numerical portion, right? So this resistance is directly proportional for the higher temperatures. This resistance is directly proportional to this temperature, and that is given by this relation. This is right. And yeah, so you can see that this R is directly proportional to T, where this alpha is the temperature coefficient, right? So okay, so this is the relation, and we can also write the resistivity in same manner. This one is the important relation And let's say we are increasing, let's say that a particular wire is at some resistance. Let's say this is at some resistance R1 and it has a temperature T1, right? And from this R1 and T1, you are increasing the temperature of this resistor to a new temperature, and that is T2, right? And the new resistance at T2 temperature would be R2, where this T1 is smaller than this T2. So you're increasing the temperature, right, of this so now you can calculate directly this temperature coefficient, and that would be equal to R2 minus R1 divided by R1 T2 minus T. So this is a very important relation. Okay. In this way, you can calculate the temperature coefficient, right? This is part clear.
So this formula will use for resistance and the above ones what we use for.
Yeah. So okay. So let's say that you are given an absolute temperature, right? So at this temperature, this is the resistance. At initial value, this is the temperature, and at this temperature, this is the resistance, right? And then you want to calculate the resistance at some specific temperature. So then you will use this and this one. Let's say you have let's say you have a resistance which is at, let's say at 20 degrees C, the resistance of a wire is 30 ohm, right? Now you want to find out, let's say you are saying that the temperature, so at 40 degrees C, the resistance has become 90, right? Then you want to find out what is this temperature coefficient. Then you will use this part. Is this clear?
Yes.
Okay, so now let us do a question, right? So in the CPSC part, you have done this nichrome wire, nichrome heater question, right? There was
Yes,
this,
I think so.
yeah. So you just go through that question. Now let us do this different question. So we have a resistor whose resistance is let's say 120 ohm at 20 degrees, right? And after increasing the temperature to 40 degrees, the resistance has become, let's say, 200. So find the temperature coefficient. Right. So in this question, what formula we'll use? We'll use this one, right?
Yes.
So R1 is given. R1 is 120 ohm and T1 is 20 degrees and R2 is 200 ohm and T2 is 40 degrees, right? So then we can directly calculate alpha, and this would be R2 minus R1 divided by R1 and then T2 minus, right? So this would be how much? 200 minus 120 divided by 40 minus, there is R1 also. R1 is 120 and then 40 minus 20. So this would be how much? 80 divided by 120 into 20. So this part cancels. This is 4 and this is 30. So 1 by 3 into 10 to the power minus 1, which is 0.3 into 10 to the power minus 1, so this is 0.3. Right. So this is the temperature. Is this part clear? Sorry.
Yes, sir.
Please note down this part.
Yes. So can you show the question? I have noted.
Oh, yeah, what?
Can you show the question? I have noted this down.
Yeah, so this part, please note down this part and then don't note down the question, right?
Yes, a question I have.
This part, please note it down, and after that, please.
So I have written this part. Can you show the
Oh,
question? Yes,
oh,
sir.
so you have already. Please. You have another question which is. Okay, whenever you have noted down, please, let me.
So yes, just now say unit for this one.
Yes, just.
So just now say unit.
Yeah, this is the third unit, right?
Now, sir, is there no SI unit?
Oh, yeah. So you see that what is this? So what would be the SI unit, right? This is
Yes.
alpha, right? And
Sir.
yeah, so this is your alpha, right?
Yes. Sir.
And you have this alpha is R by R naught, right?
Yes. Sir.
So this would be per degree C, right?
Yes.
This would be degree C minus 1 because you see that the dimension of resistance will cancel out, right?
Yes.
So
Sir.
then this would be degree C inverse. Yes. Because you have this, so dimension of alpha would be 1 by T, right? So which means that degree C. Yeah, so did you note down this part?
Yes, I noted down.
Okay, so now the next question is that let's see that what happens when you join two different materials of wire, then what will happen to the temperature difference? Okay, this is the question. So you have let's say you have two wires, right? So you have two wires have same resistance at 0 degree, right? So you have this wire and this another wire. So let's say this is wire 1 and this is wire and at 0 degree C, at 0 degree C, this has R, let's say R naught resistance, and at 0 degree C. So what would be the resistance of this wire? Right, same resistance. So R naught. Is this clear?
So can you explain again?
Yeah, so you have two wires and it is given that they have same resistance at 0 degree. Oh, so Chavez has. Yeah, so you have two wires and they have same resistance at 0 degree. Okay, which means that this is wire 1 and this is at 0 degree C and this is also at 0 degree C. So let's say that resistance is R naught. So what would be the resistance of this one? That would be also R naught, right? Is this clear?
Yes, sir.
And if I connect them, so at 0 degrees, at 0 degree C, I connect them in series, right? So this is R naught, this is R naught. So what would be the equivalent resistance? Let me write it as R equivalent naught. So what would be that? Yes, Chavez. Tarif and Chavez, guys. So Chavez, we are talking about the temperature dependence of the resistance. So we are using that. This is R naught 1 plus alpha T minus Z. This is what.
Sorry, sir. I had to go for Salah, so can you scroll up, sir? I'll just take a screenshot.
Okay, yeah. So then wait to get disconnected. So in here you got disconnected, right? When we were doing this problem.
Follow this, sir.
So yeah, please take the screenshot of this part.
Sir, I wrote this, sir.
Oh, the full question you wrote.
This whole answer I wrote, sir.
Oh, so then please take the screenshot of this question. Okay. And then please take this is screenshot, right? And then we did this problem.
Scroll up.
Oh, scroll up. Is
Sir,
it
little bit more.
little more? Yes, taken.
Uh, yes, sir. Done.
Then please take this screenshot. This is very important relation. Right, this one is very important relation. So how can you calculate this temperature coefficient? Right. Okay, then this was the question that we did. Yes, taking the screenshot. Yes, Chavez, did you take the? Okay, now we are doing a problem, right? We are doing a problem in which there are two wires, right? There are two wires which have the same resistance at 0 degree, right? So the first one has a resistance R naught. So the other one has same resistance, which will be R naught again. and I am connecting them in series at 0 degree. So in series, what is the R equivalent, guys? What is R equivalent? Let's say this is R1, this is R.
Yes, R0.
Yes. R1 plus R2, right? In series combination. Right, guys?
Yes.
So this would be 2R. Okay, this part is done. Now, at some temperature, the temperature coefficient is alpha 1 and alpha. So the question is that what is the equivalent temperature coefficient? Right, so when we connect these wire at some temperature, let's say at some temperature T, so this one will have R1 resistance and this will have R2 resistance, right? So we have to find out this one has alpha 1 coefficient and this one has alpha 2 coefficient. So we have to find out that what is the relation or what is the alpha equivalent. Is this question clear? Right.
Yes.
Okay. So
Once again, repeat the whole question.
yeah. So the initial part was that these two wires were at the 0 degree temperature, right? So at 0 degree, the resistances were same. Now, then we calculated the equivalent resistance at the 0 degree temperature, right? So then what we do is that now we have connected these two wires at some temperature. So these wires will have some temperature coefficient, right? So the question is that what is the equivalent temperature coefficient if they are connected in series? Yeah, so we want to calculate what is the equivalent temperature coefficient when they are connected in series. So now again, what do we know? We know that R1 would be R naught 1 plus alpha 1 T minus T naught. And T naught is how much? 0 degrees, right? T naught is 0 degrees. So let me directly write as, okay, so I will put the value after later. So R2 is how much? R naught 1 plus alpha 2 and T minus T naught, right? So, and R equivalent would be how much? This would be R equivalent naught 1 plus alpha equivalent T minus T naught. Are these three equations clear?
Yes.
So now I have connected them in series. So in a series, R equivalent would be how much? This would be R1 plus R2, right, guys?
Yes.
So R equivalent, let us put all these values. So R equivalent naught and 1 plus alpha equivalent T minus T naught, and this would be equal to R naught 1 plus alpha 1 T minus T naught and R naught 1 plus alpha 2 T minus. So then R equivalent naught I already, how much is that? So that is 2 R naught. right? So let us put that value. So 2R naught, and this is 1 plus alpha equivalent T minus T naught, and T naught is 0. So let us put that value. So this is T, and then R naught 1 plus alpha 1 T plus R naught 1 plus alpha 2. So this is 2R naught, and this is 2R naught alpha equivalent T. This is equal to R naught plus R naught alpha 1 T plus R naught and R naught alpha 2 T. So R naught plus R naught 2 R naught, so that will cancel, right? So I have 2 R naught and alpha equivalent T equal to, I can take R naught and T common. So this is alpha 1 plus alpha 2. Right, so then alpha equivalent would be how much? R naught T alpha 1 plus alpha 2 divided by 2 R naught T. So this part will cancel out and we'll have alpha 1 plus alpha 2 by 2. So whenever we connect two resistances and they are of different material, they are of different kinds of temperature coefficient, then the overall temperature coefficient is this. Is this part clear?
Yes.
Yeah, so then please,
Repeat once what you said now.
yeah, so I am saying that you connected two kinds of, so this one was one kind of wire and this was of the other kind of wire. And then you connected them in series, right? And then you are increasing the temperature. Then overall, so this wire has this temperature coefficient, right? This has different property. This wire has different temperature coefficient. And when you connect them in series, then the overall coefficient would be alpha 1 plus alpha 2 by 2. So this is what I'm saying. Is this part clear? Okay, so please note down this part. Please note down. And whenever you guys want me to scroll down this clip, yeah, whenever you guys have noted it down, please tell.
It's a pen school time.
Yeah, whenever you guys have noted it down, please. Noted, guys. Yes, guys, noted.
So 1 minute.
Oh, Davies has noted.
Yes, sir.
Good. So now we know that how this resistance is related to, right? How this resistance is related to resistivity, length of the wire, and so now let us do some question based on this. So we know that this R is rho L by A, right? Okay. So now we have and this is this is the length of the wire, right? And this is area of cross section. Right. So now let us do some question based on. So we have first one, maybe you guys have done in your CBSE portion, right? So let us do this again. So we have a cuboidal like a Y, right? So we have this cuboidal like wire, and how many surfaces do we have in cuboid? Yes, guys, how many surfaces do we have? So six, right? So we have this surface, we have this surface, right? We have opposite to this one, we have this surface, and then we have this surface, and then we have this one. Okay, then this would be not this, right? This one and this one, right? And then the last one. So then we have, how do I paint that? So then this bottom one, okay, and then this top one. So I will just write them down and you guys understand that what surface I'm talking about. So this is first surface, this is second, this one is third, and opposite to that is fourth, and then this one fifth, bottom, and then the sixth one, this is this one, right? Okay, so let's say that what is the dimension of this cuboid? So this is length. Let's say this is L, or let me denote it as E, and then I have this breadth B, and then this height C, right? So is this part clear, guys?
Yes.
Okay, so now the question is that I want to calculate the resistance between one and two surfaces, right? So is this part clear? And let's say that the resistivity of this material is rho. So resistivity is rho. So did you guys do this problem in your CPSC course?
No, sir.
You have done this problem.
We didn't do this question.
Oh, you guys didn't do this problem. So let us do this problem. So we want to find out what is the resistance between first and second surface, right? So let me show you guys. What is the resistance? So I have this surface and this end one, right? This surface and this surface. So this has, let's say this one is what? This one is the length, right? This one is the length. This one is the breadth, and this one is the height, right? So I can choose, let's say this is the height and this is breadth. So then what is the resistance between this surface and this surface, right? So let us try to find out that. So that would be rho L12 divided by area A1, right? Is this part clear?
Yes.
So you guys tell me what is the length from 1 to, what is the length?
BC.
Length. Yeah. So from here to here we are going, right? This is length is. Did you understand this part, Tariq?
Yes.
And what is the area of cross section? Yeah, absolutely right. And what is the area of cross
Sir, what
section?
is it?
What is A? So this is the length of this wire, right? This cuboid like wire, right? So let's say, yes, C. C is the height of this cuboid, right? Length, breadth, and height. So let me show you in this box. So then it would be. Okay. So you have this box with this. You have this cuboidal box, right? And this has this surface, this surface, this surface, behind one surface, and the up surface, right, and the down surface. So let's say that this is your length, right? This is your length, and this is your breadth. This is length, this is breadth, and this is your height of this box, right? So if I am calculating this surface area, so what is coming in this part? And if I'm calculating the from here to here, so what is the distance between these two? The distance between these two is this one, right? These two surfaces, the distance
Yes.
between this surface and this surface. So this is the distance, and that is A, right? This one I have called it A. This one I have called it B, and the height I have called it C. Clear? Clear is this one? So now if I'm talking about this surface, I have talked about the length. I have talked about the length, right? Length between these two surfaces. Now I'm talking about the surface area of cross section. Area of cross section. So this is what? This is what? This is what, guys? This was B, right?
Yes.
This was B, and this was what?
C.
C, right? So then you guys good. So then you guys understood that what would be so what would be the area of cross section of this part, right? So this would be BC. Is this clear, guys?
Yes.
Okay, now if I ask you that what is the resistance between 3 and 4, right? So 3 is this one. Let's say you have these walls, right? So the opposite wall, this wall you have calculated, and now you are calculating this wall with this one, right? So we know that this is C, right? And we are talking about this wall, right? This is how much? A.
Yeah.
So what would be the distance between this wall and this wall? What would be that? What would be the length? Yes?
Row AC.
No. The length between 3 and 4 surface. 3 and 4 surface.
A.
A.
C.
Think about it. Think about it. So you guys have the ratio. Now, what is the surface that you have? So in the previous case, I talked about this one and this one, right? Now I am talking about this one, this front
Okay.
wall. So this is the front wall, and this is the back wall. So what
I
is
thought
the
you were talking about the top and the bottom.
no. Top and bottom are yeah. Top and bottom are so top and bottom are 6 and 5.
Yeah,
Right.
okay.
Yeah.
And then 3 and 4 will be
Opposite
C.
wall.
No, B.
Yeah. Yeah, so 3 and 4 distance would be B. Yes, absolutely right. So 3 and 4 would be B, and divided by area would be how much?
AC.
AC, right? So this is, and if I'm calculating R 5, 6, so then this would be 5 and 6, right? Top
So,
and bottom. So C by
AB.
good. So this was the resistances of these surfaces. So please, do you have any doubt?
No, sir. It's clear.
Yeah, so please note it down, and then imagine this thing with some box, or you can also imagine this with your room, right? So your room is cuboidal shape, and there are 4 walls, right? And there are ceiling and this bottom surface, right? So you have this floor, and then you have this ceiling, and then you have these 4 walls. So the resistances between the opposite walls and the ceiling and the floor. So when you imagine that, then this would be right. Sorry. Yeah. So please note down this problem and where did Chavez go? Whenever you have noted it down, please.
Yes, certain.
Okay. So the next question is. So we have a similar kind of question, and we have to calculate why this is not. What So now I have a question like so I have a hollow conducting. Oh, so Chavez has it, right. Oh, then you got this. What is happening with Chavez? Okay, so we have a hollow conducting wire with inner radius A and outer radius B. Then the question is that what is resistance? First question is between the end of the wires and second one is between the the curvatures, right?
I got disconnected, sir. Can you scroll up?
Yeah, so your voice is breaking, Shavi. So yeah, this way. Yeah, did you take the screenshot, Shavi? Yes, Chavez, did you take the screenshot?
Can you hear me, sir?
Yes, yes, I can hear you.
Hello,
Yes,
sir.
yes, I can hear you. Yes, Chavez. Yes, yes, I can hear you. So, do you have any question in this part? Any doubt in this question? Yes. Now I cannot hear you, Chavez. Yes. Can you hear Tarif? Can you hear Chavez?
No, sir. I think it's not.
Hmm, maybe.
Meaning of R34, like, what do you say?
Oh, so you want me to talk about this 3-4, right? How do we calculate this 3-4? Yes. Was that your question? Yeah, Chavez. So I cannot hear you, Chavez. Yes. Are you saying something, Chavez? Yeah, you got disconnected. So the question is, in this question, we have a hollow cylinder. So we have this cylinder, and then we have this right. And then we have this one, right? And then we have this. Okay, so this is a hollow cylinder. This part is empty. So this portion is, so we have this cylinder whose only this part is
Sir, can you hear me now?
yes, yes, yeah, I can hear you. Yes, of course I can. Yeah, so do
Sir,
you
can you
have,
just scroll?
yeah, yeah, yeah. So let me scroll it up again. Okay, one moment, yes. So yeah, in this
Sir, here, like, how do you pronounce R3 first, sir?
yeah, so 3 4. So let me show. So as we talked about that this is our A, this is B, and this is C, right, Shavi? Right? So then we calculated this part and this part. So this I said 1 and 2. And
The resistance of a cross section.
yeah, so area of, yes, your voice broke in a bit. So 3 and 4 are this one. This is 3, and this one. This one is 4, right? And then top and bottom are 5 6. So this is 1 and 2. This is
Like
3 and
R3 4 is the area of cross section.
yeah. So area of cross section would be this one. This is 3 surface. So the area of cross section of surface 3, and that is equal to area of cross section of 4. So area of cross section at the end, we are calculating that. And 3 4 would be, yes. So what happened? Yeah. So what happened to, he got disconnected again. What is happening? Yes, yes, Shavis. So 3 4 is this one. This is A, and this is C. So AC, area of cross section is AC. Is this part clear, Shavis? So is this clear how this is AC? Okay, then we are doing this next question. So one part we can do, right? One part we can do. And in this question, first we have to calculate the resistance between the end of. So first we have to calculate. First we have to calculate the resistance between this part and this part at the end of the wires, right? So at the end of the wire, let's say this length is L, and let's say this is A, and this one is B. So inner radius is A, outer radius is B, right? Okay, so this I can also paint it out, right? So this one and so I have to calculate the resistance between, let's say this is 1 and then this is 2. So I have to calculate the resistance between 1 and 2. This is first question, right? So this resistance would be rho L by A, right? And this rho is there, L is this distance between this 1 and 2. And what would be the area, guys? So this is our cross section, and this is hollow. So what would be the area, guys? What would be the area? This part is
Maybe square minus pi a square.
yeah, so pi, and this is b square minus a square, right? So area of bigger circle minus area of smaller circle, right? Clear? Is this clear? Is this clear? So for the bigger,
Yes.
yeah, so for the bigger one, the radius is b, and for the smaller one, this is the radius. So this would be pi b square minus a square, right? So this is the first part. Now in the second part, we have to calculate the resistance between this inner inner cylinder and this outer cylinder, right? So I have to calculate the resistance between this inner cylinder, right? And then this outer cylinder. So what is the resistance between this cylinder and this one? So what I will do is that first I will take a very small, so for that case, I will take a very small so to calculate the resistance between this end and this end. And you remember these are curved surfaces, right? So I have to calculate. So how should I show this one? So this is the cylinder, right? And I have to calculate the resistance between, let's say, this one is the outer plate, and then the inside plate. Let's say the refill, right? So I have the refill now. So this one, and then this inner one, right? Let's say this is empty. So this one and this outer one. So this I have to calculate, right? Which means that I have to calculate the total area, right? So how much is the total area? So I will take a strip, right, at some distance x, and then what I will do is that I will integrate this strip. So this is at distance x, right? And then I will integrate this strip to from A, from here to B. So then my small resistance dr would be how much? This would be rho dx, right? And then area would be, so this is how much? What is the area of this cylinder? Curved surface area. So that would be 2 pi x and this L. So is this part clear? I have taken a small, very thin curved surface area, and then I will integrate this total surface area. So is this part clear? Yes, guys, this is part clear. I am no longer
Yes,
calculating
sir.
the, yeah, so I am no longer calculating between this one. I am calculating between this curved surface and the outer curved surface. So first I will take a small curved surface, right? At x distance, I will take a very small curved surface, and then I will integrate this one from A to B. So that will give me the whole resistance. So this would be integration of dr and this would be rho dx divided by 2 pi x L, and this is from A to B, right? So then this is R. This would be rho is constant, 2 pi L is constant. So then this would be integration of A to B 1 by x dx. And what is this integration, guys? What is integration of 1? Oh, so you are saying, can I repeat? So should I, which portion do you want me to repeat, Chavez? Yes. Oh, so you understood, right? But you guys tell me, what is the integration of 1 by x? 1 by x. So that is integration of 1 by x is ln x.
Log X.
Yes.
ln.
So ln x. Then this would be how much? So this would be rho by 2 pi L ln x from B to A. So this is rho by 2 pi L, and this is ln B minus ln A. So what is log B minus log A? That is ln of B by A, right? So is this part clear?
Yes, sir.
Okay, so please note down from here, right? Please note down, and if you have any doubts, so please ask. So we'll stop at here, and in the next class, we will do cells, combination of cells, and Kirchhoff law. So then we will quickly finish this chapter, and then yeah, whenever you want me to scroll down, screen, please. Yes, noted, Sadi.
It's on.
Oh, oh, Chavez, you have come. Yeah. Oh, yeah. So we didn't do any question further. We are just please note it down. Oh, so you
Yes,
already
certain.
now we are calculating this second right. So you already noted, Chavez. Then we will stop it here, and